All right, let's look at using the Nernst equation to calculate non-standard cell voltage. Well, what does that mean? Well, we've looked a lot at cell voltages and calculating Ecell and standard conditions. But standard conditions is at a certain temperature and 1 molar concentrations. Now, even if you start there, it's going to change pretty quick unless you're doing something to manipulate that. So this is a good understanding of what, how that cell voltage can actually change and why things like batteries, the voltage changes as they get used up and things like that, because the concentrations change in the chemistry, and so your voltage goes down, which is why we can use voltage to understand how much like a primary battery has left. So let's take a look at what's going on here. There's a lot. The first thing I'm going to do is write the equation here that I'm using, the Nernst equation. So that is E equals our standard cell voltage minus our gas law, temperature, number of moles of electrons, Faraday's constant times natural log of Q. Now, that Q tells me I need to write an equilibrium expression. So let's figure out what Q will look like. Q will look like, and again, we're not going to use our pure liquids, our pure solids. So I'm going to say manganese 2 plus squared times 5th power for lead. And then we got another squared and hydrogen. So pretty big equilibrium expression. Okay, so let's work through this. First thing we got to do is find our what's being reduced, what's being oxidized. So I see -8 here. So this is a +7 to get to that -1, +1 for hydrogen. We have a 0 here. Here we have a +2. There's our reduction. Here, hydrogen's +1. And then we have a +2 from 0. So there's our oxidation. So let's look this up. So we're looking for a manganese reduction and a lead oxidation. Now remember, it's always reduction potentials. Okay, so we're looking for reduction potentials. Here's our first one. That lines up, right? We don't want to do this one. We're looking at the manganese plus hydrogen. So we got a +7 here, and we got a +2 here. So we're going to do 1.507. So we'll write that. And the reduction happens at the cathode. So this is our cathode, and it's positive. Then we got to find our lead, and there's that. So it's 0. So here's the reduction. Again, this table is always reduction. So it's going to be -0.126. And this is the anode. Anox, our red cat. So oxidation happens at the anode. Okay, so we can calculate our Ecell equals a cathode minus anode, reduction potentials. So we get Ecell equals 1.507 minus a -0.126, which gives us 1.633 volts. Okay, so that is our number here. Then we have a lot to figure out for the rest of this. We have the values for Q we can plug in that were given to us. But the big unknown, so R, we know, T, we can is going to be 298. Don't forget Kelvin. Faraday's constant is constant. So we're looking for this N. So to determine electrons, let's look at one of our half reactions. One of them is 5 Pb to 5 Pb2 plus. Now, so we have 10 plus over here. So we're going to have to add 10 electrons to balance those ions. Now we could look at the other one too. And we have 14 plus over here and 4 plus over here. So we would have to add 10 electrons, right? And you can't have a balanced equation here without the electrons balancing. But this 10 electrons is what we're looking for. And we can't just see that. So breaking into half reactions can be helpful. And that's to figure out this. Okay, so we have everything we need. We just need to plug it in. So we have E equals our 1.633 volts minus, now we're going to start with our gas constant. We're going to use our less used one, but 8.34. We've seen that number. This is joules per mole Kelvin. We like the joules in there. Then we got our 298.15 Kelvin. Most of these types of problems have that temperature. Then we're going to do our 10 moles of electrons that we found, multiplied by Faraday's constant. There's two options, coulombs per mole. We are going to cancel units by using the joules per volt times moles of electrons, but same number, so 9.65 times 10 to the fourth. This is joules per volt, mole of electrons. So we cancel our Kelvin, our joules. We're left with our volts times our natural log of Q, which is 2.13 squared, 7.68 to the fifth, 5.29 to the squared, and then 1.93 to the 16th. So a lot of calculator work here that you have to do in the right order. You might start with the natural log. Make sure you're using your parentheses correctly. That's going to be one of the bigger challenges of this type of problems. Okay, so I get 1.633 volts minus a negative 0.00551. Subtract the negative and I get 1.6385 volts. Now it says 3 significant figures, so I'm going to go with 1.64 volts, which if I look at my original Ecell would have been 1.63. So goes up a tiny bit based on the current concentrations. And remember, if you start, so your Ecell voltage is when it's at 1 molar, which is not typically where we're going to start. You want to start with more reactants, less products. And so you want to often start with a higher voltage than what it's rated to, and then it will decline. So, 1.5 volt battery might start higher than that and then end a little bit lower than that when it runs out of energy. Okay, so let's put that in. There we go. A lot to it, a lot of work, a lot of calculator efficiencies you got to work out, but you can get there.